Reciprocating compressors require both a suction valve and a discharge valve for each cylinder. The valves give the compressor its ability to pump refrigerant vapor against a pressure difference. The valves are usually located in the head of the cylinder, in passages that are connected to the high or low pressure side of the system. Now, let's follow the compression process in a single-cylinder reciprocating compressor during one complete revolution of the crankshaft. Starting with the piston at the top of its stroke, or at top dead center, the piston begins to move downward as the crankshaft rotates. Because both valves are closed at this time, the downward moving piston reduces the pressure in the cylinder. As soon as the pressure in the cylinder falls below the low side pressure in the suction line, the pressure difference will open the suction valve, letting refrigerant vapor into the cylinder. The piston continues down, pulling in more vapor until the cylinder is filled with low pressure vapor at the bottom of its stroke. Once past bottom dead center, the piston begins its upward stroke. The suction valve closes as the upstroke begins. As the piston moves up, it reduces the volume of vapor space in the cylinder. This action increases the pressure of the vapor trapped in the cylinder. When the pressure in the cylinder becomes higher than the high side pressure in the discharge line, the pressure difference pushes the discharge valve open, letting the compressed vapor flow out of the cylinder. This continues until the piston reaches the top of its stroke, and most of the compressed vapor has been expelled into the discharge line. When the piston begins its downward stroke, the discharge valve closes. The complete cycle repeats during each revolution of the crankshaft. A rotary compressor uses a rolling piston within a cylindrical housing to compress vapor against a reciprocating vane. The spring above the vane holds it in contact with the rolling piston at all times, providing a vapor-tight seal between the high and low pressure zones within the compressor. The rotary compressor requires only one valve, the discharge valve. Compression and suction occur simultaneously on opposite sides of the rolling piston, so it takes 2 full revolutions of the shaft to draw in and compress a volume of vapor. Let's start with the rolling piston at top dead center. As the eccentric shaft rotates the rolling piston from top dead center past the suction port begins to open and a space begins to form between the vane, the rolling piston, and the housing. With continued rotation, the volume of this space increases, reducing the pressure below the low side pressure in the cycle. Vapor is then drawn in through the suction port. This continues for a full revolution until the compression volume is filled with suction vapor at low pressure. During the next rotation, the suction port is blocked by the rolling piston. The low pressure vapor is then compressed in the space between the rolling piston, housing, vane, and discharge valve on the other side of the piston. Initially, the discharge valve is closed, trapping the low pressure vapor for compression. Continued rotation of the rolling piston along the inside of the housing reduces the volume of the vapor, compresses it against the vane, and raises its pressure. When the vapor pressure exceeds the high side pressure, it pushes open the discharge valve. Discharge continues until the rolling piston completes the full revolution and has expelled most of the high pressure vapor. The discharge valve closes when the rolling piston reaches top dead center. Viewed from the end, the screw compressor has 2 helical, that is, screw-shaped rotors. One is a male thread, while the other is female. Their shape allows them to compress refrigerant gas as the threads of the 2 screws mesh. The compressor motor drives the male rotor, which in turn drives the female rotor. The design, pictured here, has 4 lobes on the male rotor and 6 on the female. Therefore, the male rotor rotates more rapidly than the female. This visual shows the movement of the refrigerant vapor from the suction to the discharge of a screw compressor, as viewed from the top. the vapor enters the suction area of the compressor and is trapped between the two lobes of the rotors and the compressor cylinder wall. Many designs use an oil injection system to seal the clearance between the rotors and the cylinder. The screw threads form the boundary separating several compression chambers which move down through the compressor at the same time. Only one such chamber is shown here to simplify the illustration. As the gas moves along in the compressor, the compression chamber is somewhat reduced in volume. This is the beginning of the compression process. The compression space becomes progressively smaller until the gas exits at the compressor discharge in its fully compressed state. This side view shows the overall pattern of refrigerant gas flow through the screw compressor from its suction to its discharge. Like the scroll, compression is nearly continuous and the screw compressor operates smoothly. The impeller is the heart of the centrifugal compressor. It is a rotating circular disc with curved blades that is driven at high rotational speed by the electric motor. As the impeller rotates, it moves the refrigerant vapor from its suction opening in the center to its outer edge by centrifugal force. The vapor enters the suction at a relatively low velocity and leaves the outer edge of the impeller at a high velocity. In other words, the impeller transfers its rotational energy to the vapor. However, high velocity is not high pressure. In order to get a pressure increase, or compression, the vapor must be slowed down to convert its velocity pressure to static pressure. This is accomplished in the diffuser. As the high-velocity vapor moves radially outward through the diffuser, the flow area increases, slowing the vapor and increasing the pressure. Some diffusers have vanes or pipes which change the flow direction and further slow the vapor. Finally, the volute-shaped casing collects the slow-moving high-pressure vapor from around the diffuser and conveys it to the discharge connection of the compressor.
A scroll compressor is also known as a scroll pump and consists of a shell with an in and an outlet. The lower part of the shell contains the lubricant, which is used, for example, to lubricate the plane bearings. A motor sets an Archimedean scroll, which is found in the upper part of the shell, in motion. The scroll housing has an inlet, as well as a discharge port, and a fixed scroll. Here, the scroll housing is made transparent. The scroll housing has a base plate. The fixed scroll is attached to the underside of this base plate. For better visibility, only the moving scroll with its base plate and the fixed scroll are now being displayed. The gas is absorbed in the forming chambers and transported to the center of the scroll set. As the rotation progresses, the chambers become much smaller, so that the gas is compressed within the compressor. Therefore, this type of compression is called internal compression. In the middle of the scroll housing, which is shown here in green, is a discharge port, through which the compressed gas can escape. Normally, there is also a check valve.